So now that we have kind of a familiarity with the concepts of nullclines, we're going to perform a similar qualitative analysis for the model proposed below. Specifically, we need to find all equilibrium points, all nullclines, sketch them in a phase plane, and use arrows to describe the trajectory within each bounded region. So here we have our first and second equation. We see that these are definitely nonlinear. We'll have an interaction term, but we also have a squared dependent variable, so that's a big red flag. And we find our equilibrium points by setting both equations equal to 0. We have 4 equilibrium points. In order to know what they are, we have to compute the Jacobian matrix. The Jacobian matrix will be, the top left component will be the derivative with respect to x of this guy, and the top right component will be the derivative with respect to y, which will give us 2 minus 2x and negative x. And the derivative of dy dt with respect to x is negative 2xy, and the derivative of dy dt with respect to y is 2y minus x squared. So I'll just start with the first equilibrium point here, plug that into the Jacobian matrix. I get 16, 2, 16, and 4. And I encourage you to verify all of this, plug it back in, and make sure that you agree. Before we compute eigenvalues of this to classify it, we have to check its determinant and make sure it's not 0. So it comes out to negative 8, which is fine. Now we can compute and proceed to get the eigenvalues, and we see that we get 2 real eigenvalues, which means that the theorem still is valid. One of them is positive, one of them is negative, therefore negative 2, 4 is a saddle point. So trajectories will never end up at the point negative 2, 4 unless they start there. Now 0, 0 gives us this matrix, and the determinant of that is 0, since 2 times 0 minus 0 times 0 is 0, and that's an uh-oh moment. We can't really proceed to find the eigenvalues because we failed part of the theorem, so the theorem is going to be inconclusive. So one thing we can do is to kind of zoom in and see what's going on. And if we look at the phase plane near 0, 0, we really see that the points are moving away from 0, 0, and so it appears that 0, 0 is acting like a source. For the point 1, 1, when we enter that into the Jacobian matrix, we get a determinant of negative 2, which is fine. Compute its eigenvalues. We get 2 and negative 1, which means 1, 1 acts like a saddle point. So again, 1, 1 will kind of push trajectories away. We'll kind of suck them in and push them away. And finally, 2, 0 is another equilibrium point, and we get a determinant that is, I think in this case, the determinant of J20 is equal to positive 8. Negative 2 times negative 4 minus 0. So we can proceed. The eigenvalues are both negative, and so 2, 0 acts like a sink. Great. So now we're going to find the nullclines. So the x nullcline is where dx dt is 0. So all I've done is set dx dt equal to 0, and I get 2 solutions. I get x equals 0 and y equals 2 minus x. So this is actually, believe it or not, the same nullclines we came up with in the past problem, but x equals 0 is this vertical line here. 2 minus x is the line that goes through 0, 2 and 2, 0. It's going to look more like that. All right, there we go. And so now we need to, since this is where all the points along these pink vectors, the dx dt component is 0, we need to figure out what's happening along all these intervals. Okay, so that means I need to pick my look at my 4 regions here. I have actually 1, 2, then this region down here, and this region over here. And if I plug those points into my differential equation in each of those 4 regions, and look at the sign of dx dt. Again, the only way for a positive dx dt to change from positive to negative is to jump across one of those nullclines. So if I pick, let's say in region 1, I pick the point 2, 2, and I plug that into the dx dt equation, which is x times 2 minus x minus y. Here I'll get 0 minus 2 times 2, which is a negative value, a negative 2. So this is going to be a negative value, which means my vectors are going to point left in region 1. So I'll have leftward pointing vectors in region 1. Now in region 2, which we'll just arbitrarily call this region here, I could pick the point 1, 0. And if x is 1 and y is 0, I'll have 1 times 1 is positive 1. And so the vectors in region 2 are all going to point to the right. So that's up here and here as well, because that's not a nullcline, that's just an axis. Region 3, if I pick something over here, let's say negative 1, 0, that will come out to be negative, which means those vectors will point left. And region 4, which is here, if I pick something like 1, 1, 4, then that will be a positive value, and those vectors will point to the right. So here all the vectors point to the left, here all the vectors point to the right. I'm going to repeat this analysis. This is just my x nullcline. I'm going to do my y nullcline analysis now. So set dy dt equal to 0, and we see that we have two positions, or two places where that happens. Y equals 0, which is the horizontal line here, and y equals x squared. Now y equals x squared is actually a parabolic function, so we'll plot some points on this, negative 1, 1, and 1, 1, and then 2, 4, and negative 2, 4. So we kind of have something that looks like this, a parabola here, and that's going to work just fine. Okay, so we have, again, 4 pockets. We have this pocket, this pocket, this pocket, and everything below the horizontal axis. Again, we know that along the pink curves, anywhere along there, dy dt is 0. So if you pass through a nullcline, then you can only pass through horizontally, not vertically. And so, okay, once again, we're going to pick points in each of these 4 regions and figure out whether dy dt is positive or negative in those regions. So here's region 1. I could pick something like 0, 1, which is in that region. And if I have 1 for y and 0 for x, that's going to give me a positive number. And so this is going to be positive, which means the vectors point up everywhere above here. Now I'll pick another point, like let's say 2, 1, and at 2, 1, if I plug those points in, I'm going to get a negative slope. Again, I've done the work on this already to save some of that time. And that's, we'll call that region 2. So all the points in region 2 will have downward vectors. And then region 3 is down here, so we'll actually end up picking a point like 0, negative 1, which is this point here. And if I choose that, then I'm going to get a positive, I think. Let's see, 0, negative 1 for y. I'll get a positive value. So this will give me a positive, which means all the vectors will point up. The y component of the vectors will point up. And that's region 3. Region 4 is over here, so let's pick negative 2, 1. Negative 2, 1. And that's going to give me a negative slope. And so those vectors are going to point downwards. Now I'm going to put these two things together now and draw all the x and y nullclines together on the same graph. So let me go ahead and do that below. And so here we have just a copy of that x nullcline graph. It just helps to superimpose your work on one that you've already drawn. So I encourage you in these notes just to go ahead and draw on top, put the x nullclines on top of the y nullcline graph. And so all I'm going to do here is just go ahead and reproduce this component here like that, and also this component down here like so. And now all I have to do is just transfer all of my green vectors across those different regions of that pink line. So remember, everywhere to the top right, those vectors all have left-facing components. So that's also here, because again, we're within that region, the top right region, and same thing down here, that's going to point right. Now, as long as we are in this pocket here, the vectors all point to the right. If we're in this pocket here, we're in the region that's below the two green intersecting lines, and those vectors will all point, left. Those vectors will all point left because of this vector here. Now, if we're inside of this triangular region here, everywhere within that triangular region, the vectors point right. So right there and right there. So we have that all labeled. Now we have to get the pink components to see whether there's going to be up or down travel. If we're within this region 2 of the y nullclines, those vectors are all going to point down. So that's going to be everywhere inside of this region. So here and here. Now if we're within that parabolic region, above that parabola, all of those vectors point upwards because that's region 1. So we're going to attach upward components to all of these vectors in there. And then within this pocket, we said they all face down. Within this region, they all face up. And same thing here. That's upward because that is below. And we see that we have this all pretty well labeled. And we again see our equilibrium points. There's 1, 1. 1, 1 we said acts as a 1, 1 acts like a saddle point, 2, 0 acts like a sink, 0, 0 acts like a source. So only 2, 0 can actually suck solutions into it. 2, 0. And again, we can just see where these equilibrium points are, where the green and pink lines intersect. There's 0, 0, and we have one more at -2, 4, which is this point here. So we have another equilibrium. So that's a saddle, this is a saddle, this is a source, and this is a sink. So solutions can arrive at 2, 0. Let's take a look at a sample trajectory. So what might a sample trajectory look like? Well, what about a particle that starts in here? Where will it go? Well, it's going to go down and to the left. So one possibility is this point comes here and bumps into this nullcline. Well, that's an x nullcline, and you can see that to the right of that x nullcline, vectors point left. To the left of that nullcline, vectors point right. So there's a contradiction. That means dx dt is 0 at that point. But we see that the arrows have downward facing components. So this point will kind of break through vertically into here. And now that vector has to travel down and to the right. Well, it could come into the equilibrium point 2, 0, like so, because it's a sink. It also could actually maybe hit this pink nullcline. But that's a y nullcline. That's where dy dt is 0, and you see that there's a conflicting downward and upward pointing arrow. So that point cannot break into this region because it's a y nullcline, no incline. But we're on the right-hand facing side of the x nullcline, so this point will have to come into 2, 0. Now another possibility, of course, is that that point comes in and hits this nullcline first. That's a y nullcline. You see arrows point down below this, and they point up above this. So since it's a y nullcline, that means this point cannot go upward, but all the dx dt say that it will point right, so it'll break through there. Now this point is forced to go up and to the left, so it could go up and to the left forever. Or perhaps what happens is it hits the green nullcline, and if it hits the green nullcline, well, that's an x nullcline, so dx dt is 0, and we see that both of the y components face up, so this point is going to veer off to infinity, either like that or like this guy here. And a point that starts, say, inside of these regions, like, let's say something that starts near 0, 0, like say here, that point is going to move up and to the right. So the one possibility is, well, it can't hit 1, 1 because 1, 1's a saddle point. It can come closer to it like this, going up and to the right. It's got to hit that nullcline. That's an x nullcline, which means you see there's a leftward pointing arrow to the left of it, or rightward pointing arrow to the left of it, and a left pointing arrow to the right of it, which means the only way to pass through this is to go straight up into this region. And we already know what's going to happen here. That point's going to go off either to infinity like that, or off to infinity like that. And so all those points are just going to have an infinitely growing y component. Let's go ahead and take a look at the phase plane real quick just to see how this behavior actually comes about, or how it looks in that phase plane. So in here we have it. We can kind of see that we said that a point that starts over here is going to be relegated to hitting that 2, 0 equilibrium point. You can see that the x versus t, x hits a value of 2 and stays there, y drops down to a value of 0 and stays there for all time, and all these points seem to go to that same equilibrium point until you get above this parabola, which if we look at the point 1, 1, which is somewhere right there, we see that all those points are going up towards infinity like we described. And kind of what's going on in here, these points will go down and to the left, and those points will go out forever, because if this point hits this nullcline, that's where dy dt is 0. Both arrows point left, therefore that point should go out infinitely in that direction as well. And down in here you can see those points are going up and to the right, so likely they're going to hit 2, 0, and you see that they all do. These go to the left and up, and so everything that happens down here has to go to the equilibrium point 2, 0. Now we also have this little pocket here, and we said that if you're really close to 0 but below that parabola, you can see that that also hits the equilibrium point 2, 0. So what we've done here in this video, to recap, is a nullcline analysis. It's a way of visualizing what's going on in the phase plane and to understand what trajectories or what paths certain initial conditions may take just based on analyzing the rate of change equations. Notice that we didn't do a lot of heavy calculus. We just had to compute some vectors, and we were able to map out pretty accurately what's going on everywhere in that phase plane. So this is a very useful tool for homogeneous nonlinear systems.